Hello everyone and welcome back to another video. Today we're going to start on chapter 4 of the textbook on Fermat's Little theorem and Euler's theorem. However, before we get into proving those theorems, I want to start by explaining a crucial concept for developing them, and that is orders modulo n. We're going to introduce this concept by building up to it with a set of theorems, concluding with a theorem that supports the definition of orders, makes it a well-defined definition. So let's just start by jumping in with a brief exercise connecting GCDs and powers in modular arithmetic. So what we're going to look at is we know that the GCD of 2 and 7 is 1. So what we're going to look at is see what happens when we take 2 to different powers modulo 7. So starting with just 2 to the 0, we know 2 to the 0 equals 1. So that's congruent to 1 mod 7. Next, 2 to the 1 is congruent to 2 mod 7. Next, 2 squared, obviously congruent to 4 mod 7. And then next, 2 to the 3 is congruent to 8, but we know 8 is congruent to 1 mod 7. Next, 2 to the 4 is congruent to 16, or it equals 16, so that's congruent to 2 mod 7. And then 2 to the 5 is congruent to 32, which is congruent to 4 mod 7. Then finally, 2 to the 6 is congruent to 64, which is congruent to 1 mod 7. So what we have here, we have all the powers of 2, 1 through 6, mod 7. And one thing that we can notice from this right away, we can sort of see the cyclical pattern. It goes 1, 2, 4, 1, 2, 4, and then 1. And that pattern is actually going to continue. Adding 1 to the power just multiplies it by 2. So what happens to this 1 is going to be the same as what happened to this 1 back here and to this 1 back here. It'll become 2, and then it'll become 4, and then back to 1. So that cycle is going to continue. But to understand why that'll continue, we need the concept of orders. And now that we have that exercise out of the way, let's start proving some theorems about powers in modular arithmetic to kind of develop this definition of orders. So the first theorem that we're going to go over is theorem 4.2. And this theorem states, let a and n be natural numbers with the GCD of a and n being 1. Then the GCD of a to the j and n equals 1 for any natural number j. Okay, so then for our proof of this, we're going to start by just letting a and n be natural numbers with GCD of a and n being 1. And what we want to do is show that a to the power of j equals 1. Actually, so we're going to define j in this line as well. So a, n, and j are all naturals with GCD of a and n equal to 1. Now, obviously, 1 divides 1. So by theorem 3.20, which is the one about solutions to these modular equations, ax is congruent to 1. So the linear congruence here, modulo n, has a solution. Okay. And by theorem 1.18, ax to the power of j is congruent to 1 to the j mod n. Therefore, a to the j, x to the j is congruent to 1 mod n. So a to the j times y is congruent to 1 mod n for y equals, let's scroll down slightly, y equals x to the j. And y is an integer. So we know that this linear congruence for a to the power of j is congruent to 1, and by theorem 3.20, that would imply that the GCD has to divide 1, so the GCD would have to be 1. So by theorem 3.20, a to the j and n, their GCD is 1. Okay, so let's go back. What did we just prove here? This theorem is essentially stating that taking powers of an integer will not create a common factor with another integer if no common factor already exists. And that principle should be relatively intuitive if you understand the fundamental theorem of arithmetic. It should pretty easily follow, because if two numbers don't have a common factor to begin with, just creating more powers is not going to create a prime number in that prime factorization that would be necessary for there to be a factor in common. And then this proof as well demonstrates that using some of the theorems that we've proved, that we proved in the previous chapter about modular arithmetic. So that is that. Basically saying no matter how many times you take a power to something, you're not going to make the GCD not 1. So that's the first theorem. The next theorem that we're going to prove, let a, b, and n be integers with n greater than 0 and GCD of a and n equals 1. If a is congruent to b mod n, then b is congruent to, or b, GCD of b and n also equals 1. Basically, this theorem is saying reducing a number modulo n won't make a common factor appear either. Any numbers that are congruent to each other modulo n, there won't be a new common factor produced. Like it's still going to be co-prime. So our proof of this, we're going to let a, b, and n all be integers. I don't know if you guys can hear the cats in the video, but they love meowing at the door. But n greater than 0, GCD of a and n equals 1, and a is congruent to b mod n. And then by theorem 3.20, ax is congruent to 1 mod n for some x congruent to, or x being an integer, for some integer x. Okay, so still using theorem 3.20. This theorem is going to be used constantly throughout this video, so I would highly recommend just going back to my previous video where we proved this theorem. I believe that is episode 12, just to get a full understanding of what's going on with this theorem. It's a theorem that has to do with linear congruences. And I mean, that's the thing with all this stuff in math, is so much of it is just building off of itself. so much of this, like the stuff that we're talking about, you'd get such a richer picture just going back and viewing the whole course. But for this particular concept, I would recommend that video on linear congruences if you want to understand this stuff better. But yeah, so there's that theorem, and then basically all it's saying though is that for a linear congruence, for a times x to be congruent to 1, to have a solution x, it would need to, this number would need to divide the GCD, or the GCD would need to divide that number, sorry, other way around, by theorem 1.14. And since it's equal to 1, if GCD would have to divide 1 between A and N, the GCD of A and N would have to divide 1. That means that the GCD is 1, because there's no real other options. So by theorem 1.14, b to the x is congruent to 1. So we can just sub in, since a is congruent to b, we can sub into this multiplicative multiplicative product here. We can sub in b for a, and that's by theorem 1.14. So then, finally, just using theorem 3.20 again, thus the GCD of b and n equals 1 by theorem 3.20. Okay, so that's that point. And that basically just proves, as I said before, by reducing a number modulo n, or by finding a number that's congruent to another number modulo n, you're not going to get rid of the number being coprime. You're not creating a new common factor there. Okay, so that is theorem 4.3. And then we can close that off. And there's no more room there. So what we're going to do now is move on to the next column. And then the next theorem that we're going to prove is theorem 4.4. And this one is going to have a bit more interesting of a proof than the last two. The last two were really just heavily reliant on that linear congruences theorem that we proved. But let a and n be natural numbers. Then there exist natural numbers I and j such that, or hold up, with I not equal to j, such that a to the power of I is congruent to a to the power of j mod n. And if you remember before, sort of the motivating example here, thinking about how these powers create kind of this cycle, 1, 2, 4, 1, 2, 4. This is a pretty crucial theorem involved in this, kind of showing that for any a, you can find two different numbers with the same power. Kind of showing that if you take a to the power of, you can find two pairs of powers where they're equal. So that's a pretty crucial theorem and kind of supporting this idea of cyclicality that we laid out here. So let's see the proof of it. So we're going to let a and n be naturals. And let n be the canonical complete residue system mod n. So n equals this set and the cardinality of n, or the size of n, is just n. Okay. I'm making it worse by trying to correct my ugly looking n. Yes. Okay, so the size of the set is just n. There's n elements total within it. Now, by theorem 3.14, and this is a theorem about complete residue systems, a to the power of k is congruent to t mod n for all k and t in the set of all naturals. Or wait, sorry, that's not the correct statement. For some t in the set of all natural, or sorry, not in the set of all naturals. For some t in n, for all k in the set of all naturals. Basically saying that anytime you take a to a power, it has to be congruent to some element inside of n. So that's that point. And then what we're going to do next is we're going to let a equal this set. A to the 1, a to the 2, dot, 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 a to the n plus 1. So the cardinality of a equals n plus 1. And now those of you familiar with combinatorics are probably seeing exactly what's going on here, what I'm going to do next. But I'm going to introduce a new principle here, and then I'll explain why it applies here and kind of what it is. But it's a very intuitive principle. It's by the pigeonhole principle. And this principle basically says, just by the name of it, so say you have n plus 1 pigeons and n pigeonholes, and you have to assign all n plus 1 pigeons into one of n pigeonholes. Each of these pigeons, there's going to, basically the pigeonhole principle states that one of these n pigeonholes has to have at least 2 pigeons assigned to it. And think about why that is. The best that you can do is you start with those n pigeons and you assign all of them to a different pigeonhole. But then at that point, you've exhausted all of the pigeonholes. All of the pigeonholes have at least 1 pigeon in them. And then at that point, you have to assign that very last pigeon to some pigeonhole with another pigeon inside of it. So as a result of that, there always has to be at least 1 pigeonhole that has at least 2 pigeons in it. And if you weren't going to assign all of them in different ones, you'd have to start by assigning. If you wanted to have n plus 1 have its own pigeonhole, there'd have to be 1 pigeonhole that has 2 already in it. So I'll explain it a little bit more as well with an example of specifically applying to this problem. But that's essentially what the pigeonhole principle is. So by the pigeonhole principle, there must be 2 elements, or must be at least. I'll say at least here because that's important. At least 2 elements in A congruent to 1 element, or I'll say the same. In n modulo n. And now let's see why this works. Say for example, n equals 5. So then you have a to the 1, a to the 2, a to the 3, a to the 4, a to the 5, and a to the 6. All within A. And each of them have to be congruent to 1 element within n. These elements being 0, 1, 2, 3, and 4. All of them have to be congruent to at least one of them. By the pigeonhole principle, they can't all have their own distinct elements. Like say you wanted to put a to the 1 here, and a to the 2 here, and a to the 3 here, and a to the 5 here. And then you can put a to the 4 there. A to the 6 has to be congruent to one of these elements in n. So no matter where you put it, one of these elements in n is going to have at least 2 elements in A that are congruent to it. So you have to put it in one of these spots. And that's kind of how the pigeonhole principle works in this example. And I'll just circle that to kind of explicate how the pigeonhole principle works here. So then with this, what we're going to do is let n prime be the element in n that corresponds to 2 distinct elements corresponds to at least 2 distinct elements. We'll call them a I and a j, where I does not equal j in A. So that means that a to the power of I is congruent to n prime, and j to the power of I is congruent to n prime. And I'll just write that out now. Thus, a to the power of I is congruent to n prime modulo n, and a to the power of j is congruent to n prime modulo n. Hence, by theorem 1.11, a to the power of I is congruent to a to the power of j modulo n. And there you go. We have our example of 2 distinct powers of A that have to be congruent mod n. And this basically, all that this theorem shows is that raising a number to various products will sometimes produce the same values modulo n. Doesn't show this is necessarily the case, but it shows that it is at least the case for one example. That there's at least one example of this being the case for every pair of natural numbers. Okay, so that's theorem 4.4. And then next, let's go ahead and prove theorem 4.5. And actually, this theorem is the same as theorem 1.45 that we proved way earlier on in this course. But let's just go with theorem 4.5 for now. And what we're going to do is prove this using some of these similar techniques that we used in some of the earlier theorems, like using theorem 3.20. And also, an important thing about this particular theorem, it's going to be super useful in anything involving modular arithmetic in the future. It's essentially like a divisibility property of modular arithmetic. So we're going to let A, B, C, and N all be integers with n greater than 0. And then what we're going to do is say if AC is congruent to BC mod n and GCD of C and N equals 1, then A is congruent to B mod n. And then for our proof, it's going to be, I think, a little bit quicker than the first one that we did. A lot less algebra for sure. Our proof will be let A, B, C, and n all be integers with n greater than 0. AC congruent to BC mod n, and A is congruent to, or no, sorry, that's what we're trying to prove. And then GCD of C and N equal to 1. Okay, so that's the first point. So by theorem 3.20, Cx is congruent to 1 mod n for some x in the set of all integers. And then by theorem 1.14, ACX is congruent to BCX mod n. So A times 1 is congruent to B times 1 mod n. Then I'll scroll down a little bit just so I don't get cut off by my head again. So A is congruent to B mod n. And essentially, yeah, this theorem essentially works as a way to divide out C. If the GCD of C and N is 1, that basically means you can divide out C in a certain sense, so then A would just be congruent to B. Very useful principle when it comes to anything modular arithmetic related. It gives you just this ability to take out a term and make things equal. So then finally, now that we have all these proofs out of the way, we can finally prove theorem 4.6, which kind of gives us our basis for defining an order. Let A and N be natural numbers with GCD of A and N equal to 1. Then there exists a natural number K such that A to the power K is congruent to 1 mod n. So what does this help us with? This shows us if we have two numbers that are coprime, we can raise one of them to a power that at some point will make it congruent to 1 mod n. And that's super useful. Multiplying, being able to raise something to a power and to make it equal to 1 can help us eliminate terms in the future. If you make something like, say you have A in a term, you want to reduce it to 1, raise it to the power of K, that can turn it into 1, and then you're left with whatever's left there. You can eliminate this A term within a formula. So let's just see this proof. Let A and N be natural numbers such that GCD of A and N equals 1. And then by theorem 4.4, which we just proved, it wasn't the last one we proved, but it was the one before, A to the I is congruent to A to the J mod n for some I and j in the naturals such that I is not equal to j. Okay. And then without loss of generality, we're going to assume that j is greater than I. And if you just so happen to choose integer or naturals where I is greater than j, just reassign them. I mean, that's kind of what without loss of generality is saying. Thus, since a to the j equals a to the j minus I times a to the I, a to the power j is congruent to a to the power j minus 1, or j minus I, times a to the I mod n. So by theorem by theorem 1.11, I realized I did something inefficient in my proof, but I'll correct that now actually, or in the next step actually. But a to the power I is congruent to a to the j minus I times a to the power I mod n. And by theorem 4.2, which was the first one we proved, we can see that the GCD of a to the I and n equals 1, since the GCD of a and n equals 1. And now what we can see is that, so by the last theorem we just proved, or the theorem from earlier in the course, by theorem 4.5, we can remove this a to the I term from this multiplication. So what we're left with is 1 is congruent to a to the j minus I mod n. Because a to the I and n are congruent, or have a GCD of 1, we can essentially divide by ai on both sides, a to the power I on both sides, and remove that term. So what we're going to do is let k equal j minus I. So k obviously is a natural number. Hence, we have our result, which is that a to the k is congruent to 1 mod n. So what we're seeing is that if the GCD of a and n is 1, there's some power that we can take a to that makes that product or power be congruent to 1 mod n. A consequence of this actually is that these powers will cycle, because each time you're taking something to another power, you're adding 1 to that power, you're just multiplying it by a. So you're going to start where a to the power of 0 equals 1, and then you multiply by a, and you keep multiplying by a, and eventually get back to 1. Well, this theorem shows that because you eventually get back to 1, you're going to be at the same point where you were when you took a to the power of 0, and then you multiply again by a, 1 by a, and that gets you back to where you were at 2 to the power 1, and you keep going, and this cycle continues. So that is one of the most crucial consequences of this theorem, honestly, is that knowing the fact that it always comes back to 1, a to the power k comes back to 1, you can find this cyclical pattern within the powers of a to the power k, when a and n are coprime. So there's this pattern within the in the modular arithmetic of powers when the modular base, or the mod n is coprime with a. And what this ultimately gives us is a definition of orders. So, definition. Let a and n be naturals with GCD of a and n equal to 1. The smallest natural number k such that a to the power of k is congruent to 1 mod n is called the order modulo n and is denoted order n of a. Order of a modulo n. It is a's order modulo n. Okay. So to understand this a little bit better, let's actually do a quick example where we find the orders modulo 7. Now remember, in the very first example we did, we found that the order modulo 7 is 3. It's that first time when it gets back to 1. Let's see what we can find for the different powers, for different numbers. So first, one's order modulo 7 is 1 because 1 to the power of 1 is just equal to 1. 2, we already found that it's 3. And now let's see how we can find these other orders. And the way that we're going to do this, I'm just going to make a table kind of going through these. And what this is going to show, what the values are going to be, are a to the power of k congruent to x mod n. So the table is just going to show different values, the different values of x here. And actually, I'm just not even going to make those grid lines because that's going to take forever. So just starting with 1, if we take a to the power of 1, 1 to the power of 1, we get 1. So we're done. Our order is just 1. 2, remember, if we took it to 1, it would give us 1, or it would give us 2. Take it to the power of 2, that gives us 4. Take it to the power of 3, that gives us 8. But instead of 8, we can just write 1. Because 1 is congruent to 8 modulo n. And then for 3, 3 to the power of 1 is just 3. And then if we multiply that by 3, we get 9. But that is actually going to give us 2 modulo 7, because 9 becomes 2 mod 7. And then to take it to the third power, all we have to do is multiply 3 squared by 3. So 2 times 3 is 6. So that's 6 mod n, or 6 mod 7. 6 times 3, that's 18. Now 18 is 4 mod 7. Next, take 4 times 3, and that gives us 12. And 12 is 5 mod 7. And then finally, 5 times 3 is 15, which is 1 larger than 14, so that is 1 mod 7. So the order of 3 modulo 7 is 6. Up next, we have 4. 4 to the power of 1 obviously is just 4 again. 4 to the power of 2 is 16, but 16 is 2 larger than 14, so that reduces to 2 mod 7. And then next, 2 times 4 would be congruent to 4 to the power of 3 modulo n. So 2 times 4 is 8. 8 is 1 larger than 7, so that gives us, that number would be congruent to 1 modulo 7. So that gives us the order of 4 is 3. Okay, and then next we have 5. So for 5, you take 5 to the power of 1, you get 5. 5 squared is 25, which is 4 larger than 21. So 4. 4 times 5 is 20, which is 6 larger than 14. So that's congruent to 6 modulo 4. And then up next, you take 6 times 5, and that's 30. 30 is 2 larger than 28, so that's congruent to 2 modulo 7. Up next, you have 5 times 2, which is 10, which is 3 larger than 7, so that's congruent to 3 modulo 7. And then 3 times 5 is 15, 1 larger than 14, so that's congruent to 1 modulo 7. So then the order of 5 modulo 7 is 6. Now let's go with 6. 6 to the power of 1 is 6. 6 times 6 is 36, which is 1 larger than 35. As a result, that will be congruent to 1 modulo 7. So the order of 6 modulo 7 is 2. So that would be how you go about calculating orders. And note that this only works if it's a number that is relatively prime with 7. Their GCD has to equal 1. And obviously 7 is prime, so all of these numbers have a GCD 1 with 7. But yeah, that's how you would go about calculating all these orders modulo some number. And that is kind of what order represents here in this context. Okay, so that is everything that I have to say for this particular video. Yeah, thank you all for watching, and then next time we're going to dive into Fermat's little theorem. Probably going to be a longer video, honestly, but it should be a good one. I'm excited. So if you like the video, go down and hit the like button. There's also a subscribe button down below. Hit that as well. I also recommend donating on Patreon if you have any extra money that you want to throw at a small creator, help my channel grow, help keep me motivated to keep putting out this content, help me buy a new laptop eventually. This one's getting really old. This is the same one that I used back in 2019 when I started posting on this channel. And yeah, that's all that I have to say for this particular video, so thank you all for watching. There's also a Discord down below, I guess, which I forgot to mention. Go and join that. That's probably the easiest way to get in contact with me if you want to talk, if you want to set up a debate or ask questions about math. This probably isn't the type of video that I get debate requests for, but yeah, that's that. Thank you all for watching, and I hope to see you all in the next video. Peace.